All right, so the first thing in introduction is I have to persuade you that this is something interesting, right? Otherwise, you're not going to pay attention. So firstly, I want to persuade you that simulating quantum computers on classical computers is useful. And I mean, there are a whole bunch of reasons. I'm not very imaginative, so I only came up with 2 reasons. The first reason is up here, which is the present-day quantum computers are basically kind of rubbish. They're small, they're very noisy, they're full of errors. And so if you say the experimentalists among us have built a quantum computer, we actually want to check it's doing the right job, because it might just be producing garbage. It might be producing random noise. It might be producing anything. So, you know, before you're going to pay them millions of dollars and give them a Nobel Prize, you probably want to check that it does the right job. And the only way I know to do that is to either do the simulation by hand, by like computing stuff, or to get a classical computer to do it. And guessing, are you okay?
So the problem is that we don't see the slides. So
you don't see the slides. Aha.
Yeah.
The slides are probably the thing you want to see. To be honest. Yeah.
Because
we forgot the share screen button.
Yeah.
Okay. Minor oversight. Okay. How about now? Do you see them now?
There's a black square on the left bottom due to whatever reason.
There's a black square.
Yes, it's this one.
Yeah.
I mean, I can't do anything about this because Zoom just, you know, blacks out its own windows.
No.
Right now it's good.
Right now it's good. Okay, cool.
Yeah.
Yeah. Okay. So actually, I guess for the people online, I shouldn't use the stick. I should try and use the mouse to indicate stuff because you can't see my stick. So yeah, simulating quantum computers is very useful because, you know, if you have a quantum computer, you want to check it's doing the right job. Another reason it's really useful is that if you can simulate a quantum computer, then you can work out how to make quantum algorithms for it without actually having access to one. Because, you know, access to quantum computers is generally kind of expensive and your time is limited. So maybe, whereas access to classical computers is pretty cheap. So it's quite likely that if you come up with a fancy new quantum algorithm, you're first going to test it by doing classical simulations before you actually, you know, pay for access to a quantum computer. All right. So simulating quantum computers is super useful. Second thing, simulating quantum computers is really, really, really hard. Okay, so I don't have a good way of telling you about like CPU time or anything like that, because the scaling is really complicated to understand. But an easy way to understand it is in terms of energy. So Google estimated that to do a classical simulation of their quantum experiment would take a petawatt hour of energy, which turns out to be the energy output of Poland's biggest power station for about 20 years. So this is me trying to persuade you that simulating quantum computers in general is very, very hard. And this pretty strongly motivates trying to come up with smarter simulation algorithms, right? Because if it's going to take 22 years and the power output of a fifth of Poland, maybe you spend like a few years in advance making it better before you start doing that. So we're motivated, I'd say quite strongly motivated, to come up with smarter simulation algorithms, as smart as we possibly can. All right. For the record, this is like halfway between Warsaw and Poland, So I think we have some members of the audience in Warsaw, Warsaw and Krakow. So we have some of us in Krakow, some of us in Warsaw, and this is halfway in between this power station. Right. Third piece of motivation, and this, to be honest, is my motivation. I have to give you the other ones. But this is the main motivation, is that simulating quantum computers on classical computers is a really, really interesting problem. So the mental model I have in my head is a landscape of computations, right? So every point in this XY plane is a possible quantum computation you could do, right? And the height of this computation, the height of this point, or the landscape at this point, is indicating how hard the computation is to do on a classical computer, right? And we effectively know nothing at all about this landscape, right? It's got some hills, it's got some valleys, it has probably some mountains, and we would like to know something. We'd like to map it. We'd like to know something about this landscape. So at the moment, what can I tell you about this landscape? It's got some values in it. We know these values. We know that if your computation can be done with a very low number of qubits, then you're easy to simulate. You're in a valley. If you can do it with very small amounts of entanglement, then you're easy to simulate and you're in a valley somewhere. And if you have low amounts of magic, which I've written in inverted commas, this is a term that will be defined later, then it's also easy to simulate. what we.
But of course, you are thinking about landscapes in many dimensions. So
Yeah,
our
of course.
imagination of valleys and mountains is of course limited because we
Yeah,
have a good imagination of three-dimensional objects. And
Yeah.
we work in many dimensions.
Yeah, of course. This space is incredibly high dimensional. I just pretend it's two-dimensional because I can't think of more than that really.
So they are like hyper valleys.
Yeah.
Mountains, and everything is very complicated.
Yes.
So
why is it not just one dimension?
Why is it not just one-dimensional? Because if I have a possible computation, right? Like if I have a quantum circuit, there's many different ways I can change it, right? Like I would say that the dimensionality is at least like 2 to the n, where n is the number of outputs, for example. Yeah. Okay, so you'll note that I haven't written anything, which implies it's hard to simulate. And in fact, no one knows anything which makes a quantum computation hard to simulate. It's entirely possible that every quantum computation can be done in polynomial time on a classical computer. We think this is not the case. We strongly suspect that there are some mountains in this landscape, but actually we have no idea. No one's proved this. So I would dearly like to understand more about this landscape. And this is, I guess, my main piece of motivation for trying to understand classical simulations of quantum computers. Okay, hopefully at least some of you are persuaded that this problem is interesting. Good, so I should define what I mean by quantum computation. So for the purposes of this talk, a quantum computation is something where I stick in some classical inputs. Sorry, I should do it here for the Zoom people. I get out some classical inputs, and in between, some quantum mechanical stuff happens. So there are other definitions of quantum computations. So in some circumstances, you might be interested in quantum outputs here, if you're doing like quantum communications or teleportation or something. But for me, I'm interested in classical outputs because those are the things that I can actually read. I can't. I can read bit strings. I can't read qubits. To be more precise, here is a little example. So here on the top, we have a little quantum circuit. You stick in a gate, you stick in a state, phi, on 2 qubits. You had them at the first one. You apply this T gate, which is a little phase gate to the second one. This T gate is a rotation around the z-axis. You see it? Pardon?
And H is Hadamard.
Yeah, H is Hadamard, which is a sort of rotation of 90 degrees around an axis in between x and z. So it swaps the x and z axis, this Hadamard. This T dagger is the rotation in the opposite direction, Hadamard again. And actually the overall effect of this computation is to apply the quantum Fourier transform to your state. This is just an example. It doesn't really matter what it actually does. And then on the bottom is what I call a quantum computer, a quantum computation. So I can stick in some classical bits, x, which end up flipping the inputs from 0 to 1 and from 0 to 1. And I read out some classical bits y. So classical inputs, classical information in, classical information out, quantum stuff in the middle. This is what I mean by a quantum computer. And this is the kind of thing that I'm trying to simulate. Okay, so what do I mean finally by simulate? Well, there are four kind of generally accepted meanings of simulate. So firstly, you have the difference in strong and weak simulation. So a weak simulator basically pretends it's a quantum computer. So a weak simulator draws samples which are distributed according to the Born rule, basically. So it's a classical algorithm, and every time you run it, you get a bit string or you get an output. And this output, the probability distribution of this output is the same as the probability distribution of the outputs of a quantum computer. And then strong simulation is kind of a slightly different thing. This actually just computes some probabilities. So rather than sampling from the probability distribution, you say, I want to know what the probabilities of this output, and it goes away and computes it. And then for each of these, weak and strong, you can do them either exactly or approximately. So approximately, you allow yourself a little bit of error in the distribution you're sampling from. And approximate strong, you compute probabilities. You compute some numbers which are close to the probabilities, but might not actually be the probabilities. And so there's some motivation for this approximation thing, because obviously when you're thinking about simulation, I think the thing you'd expect is that I'm going to simulate them exactly. But like every quantum computer, every experiment, in fact, every classical computer has unavoidable errors, right? Like at any moment, a cosmic ray might come and hit your classical computer and flip a bit, and it'll introduce some error in your computation. Quantum computers actually have a lot more error than classical computers. So in general, when you're trying to simulate something, what you want to do is make the simulation good enough so that you're within the accuracy of the experiment you're simulating, right? Because there's not much point being like massively better than the experiment that you're comparing to. Yes.
My question is, with this strong simulation, is actually something more than we do with the quantum computer, if I understand correctly.
Yes, it is. Well, if you run a quantum, so I mean, you can do something like take your quantum computer and run it 1,000,000 times and get the probability, make a histogram, and then get the probabilities from that. But yeah, in general, it's a bit different. Yeah. Are there any more questions on this slide? Okay. So the things that I'm mainly looking at here are strong simulation and approximate. We do a little bit of, oops. We do a little bit of exact strong simulation, but mainly I'm interested in approximate. Yep. So here is my kind of general problem statement for approximate strong simulation, which is you give me a quantum channel, you give me an input state, you give me an output, and some positive real numbers, and I want to give you, you want me to give you a number p, which is closer to the correct Born probability than epsilon with probability greater than delta. Or for some reason, I've written it here further away with probability less than delta, but whatever. These are equivalent. So I'm allowed to be further away than epsilon, only delta amount of the time. Yeah. Okay, are there any questions about why, because this is kind of the main thing we do, are there any questions about like what this statement means or why we would be interested in it? Hopefully I motivated it a little bit.
So you assume that for any epsilon larger than 0, there exists delta such that this is true. Yes.
No. So I have I make an algorithm, and the input to this algorithm, you give me an epsilon and a delta, and the algorithm is allowed to be wrong with probability delta, which we assume is going to be very small. But you know, maybe you let yourself be wrong 1 in 1,000 times or 1 in 1,000,000 times, whatever. And if you're not wrong, so the other 999 times, it's closer than epsilon, right? These are inputs to a classical algorithm, these numbers. Okay.
And depending on whatever you choose, you expect that the algorithm will act faster or slower.
Yeah. So the idea, what's going to happen is that if you tell the algorithm, I want to have a number really, really close, and it's going to be correct a lot of the time. So if epsilon and delta are both really small, then the algorithm will take a very long time to run. And if you allow yourself slightly bigger error bounds, you're going to end up with an algorithm which runs a bit faster.
So in short, is it fair to say that large errors are unlikely?
Yes, exactly. Yeah, and you have some control over what errors you're willing to tolerate.
So large means larger than epsilon and unlikely because
because of the delta. Yeah. Or you can be more positive. You can say you're right with very high probability. You're correct with very high probability if you want to be positive. Okay. So yeah, so this is the first project I want to talk about. And this is what I spent most of last year and probably most of this year on as well. So this is a collaboration with Camille, Jakob Pashayan, who is currently in Sydney, and Stuart Bartlett, who's also in Sydney. And the aim is we want to come up with an algorithm for doing approximate strong estimation of Born probabilities for circuits made of these gates, Clifford and T. And state of the art means we want to be better than anyone else. Basically, we want to have an algorithm that's better than anyone else has made so far. And as a spoiler, we succeeded. So this is what we do. We have this algorithm. So I should mention that this algorithm, or these algorithms, because we came up with a few different things, we wrote them up in a manuscript. We submitted it to PRX like a month or so ago, maybe 2 months ago. They gave us some feedback, and we are hopefully this week going to send them an updated draft. We're going to talk to Jakob tomorrow about this. But hopefully it's getting there towards being published in PRX, this thing.
There's no restriction on the angle of phi.
No. So this problem is trivial if phi is a multiple of pi by 2.
Yeah.
But if pi is not, if phi is not a multiple of pi by 2, then yeah, it's non-trivial. Yep.
Well, sorry, we just short back. When you say trivial, basically
polynomial.
It is the Gottesman-New theorem, and it's
Yeah.
I don't know that.
Yeah. I give the Gottesman-New theorem in a few slides. So spoilers. Yeah. So this is what we do. Oh, yeah, I should say actually, thank you for mentioning it. So in general, people have focused on this problem before, where phi is pi by 4, and in some sense, pi by 4 is the hardest to simulate So it's kind of natural to focus on this. But actually, you can simplify your circuits a lot if you allow yourself to simplify. And it turns out that this works very naturally with our algorithms. It also works very naturally with some other algorithms that people published in 2019. But yeah, basically, in the old days, we used to always have phi is pi by 4. And for modern algorithms, I guess people usually don't care what the phi is. Okay. Yeah. So a little bit of recap, just so I don't talk just so this isn't completely boring. Can you tell me, put your hands up if you do know about the Clifford group and stabilizer states and stuff. Okay. So there's at least some people who don't. So okay, we have to go through. We go through the recap because some people don't.
I know what you say. We know.
Yeah. Yes, if you do know.
I know. So
You know. Okay.
yes.
Okay. Sure. Okay. There's a couple of people who don't. So I'll do the recap. So I define parity operators as strings of the one, so tensor products of the one qubit, these one qubit operators, the qubit operators, with an optional phase at the front, which is led to be 1i minus I or minus 1. And these parity operators form a group. And yes, because there's only 4 choices for each qubit, I can store it in 4n plus 4 space, and the plus 4 is to store the phase. Actually, this is plus 2, 4n plus 2 bits. My mistake. Yep, sorry. Yeah, 4 things you can do in 2 bits. This is an error. Okay. So in any case, you can store it in a polynomial amount of space on a classical computer, and that's what I care about. So here are just some examples of things. These are things I call parity operators. And if you fix the number of qubits is 4, then you have a group of things that look a bit like this with x's, z's, and i's in different slots. All right. So Clifford operations. These are just the unitaries which map parity operators to parity operators under this sort of conjugation operation here. So these are a very, very small subgroup of the full unitary group, but they are quite an interesting subgroup. So in particular, they include some of the gates I mentioned before. So the Hadamard gate here is there, the S gate is here, the C0 is here. And here I just show you what the actions are on some parity operators. Yeah, and then you can store a Clifford unitary before. You can store a Clifford unitary in a polynomial amount of space as well. And all you do is you store what the unitary does to a set of parities which generate the full parity group. So for example, if you store what the parity does to all of the x's and all of the z's, and then you can just take products of those to work out what it does and anything else. Yep. So this is in contrast to a general unitary would require an exponential amount of space to store, because the an n qubit unitary is 2 to the n squared. These guys are polynomial, so it's quite a start. This is a very, very small group, subgroup. Okay, so I say a state is a stabilizer state if I have this bunch of this n parity operators which map it to itself. So they're all eigenvectors of each of these. Sorry, it's an eigenvector of each of these operators with eigenvalue 1. Yep. And it's important that these guys are independent. Otherwise, there's more freedom than I want to allow. So yeah, here is an example. The state 0 is just stabilized by this guy Z on 1 qubit. This maximally entangled state is stabilized by these 2 guys. And this computational basis state is stabilized by these guys. Yeah, I wrote question mark here because I don't know how to write the computational basis state in this notation with tensor product signs. It's nicer in this notation where we subscript by a j to say which qubit we're operating on. Okay, so these are stabilizer states, and there's a lot of consequences with being a stabilizer state. You can say a lot of things about a stabilizer state. So in particular, just to summarize this slide, the set of parity operators which stabilize the stabilizer state is an abelian group. It's isomorphic to Z2 to the n. And so we can store a stabilizer state in a small amount of space just by storing a list of generators. So we store a polynomial number of parity operators, which then when you take all the possible products of them, generate the stabilizer group. So not only do we store them, but we can actually apply unitaries to them in a kind of very efficient way, just by applying the Cliffords to the stabilizer group elements one by one. Yeah. So stabilizer states are very good, and we can say basically the punchline. It's okay.
No.
Okay,
The
cool.
question was who is talking. So.
Oh, there's talking Carol.
Yeah.
So thank you very much.
Yeah. Okay.
Yes.
Yeah. I'm not sure. Yeah, okay. No. Yeah. So this little note here gives you not only a polynomial space representation of the stabilizer state, but it gives you a polynomial time algorithm for applying Clifford operations to them. So this gives you fairly easy, well, not easily, but fairly nicely, the Gauss-Mendel theorem, which says if you've got a circuit, it's got input stabilizer states, it's got output computational basis measurements, and in between it's got Clifford unitaries. Then you can basically say anything you want to about this thing in polynomial time on a classical computer. You can simulate it strongly, you can simulate it weakly, exactly. Yep, it's all very easy and nice. And yeah, the Clifford unitaries inside can all be written as a circuit made up of Hadamard, S gates, and C0 gates.
So then you would think that if we only use quantum computers to work with such a circuits,
yes,
then basically the gain quantum advantage is not large, or maybe does not exist even. Yes.
Yes, exactly.
So basically, it's kind of a danger for quantum computing, such a theory, unless you explain that it's good to work with other operations, other states. Yes.
Yes. So, for example, you want the T guy that I had before, this phase gate. Yeah. Exactly. And in fact, well, there's a nice characterization actually of the computations that you can do in terms of logarithmic space. Yeah, they require, these are the computations, it turns out, that you can do in logarithmic space on a classical Turing machine. For us, this doesn't matter very much, but logarithmic space is an incredibly tight bound. Like you can't do very much in a Turing machine in logarithmic space. Yes. So even for a classical computer, these computations are very, very basic. Okay, but we can break out of this kind of prison that we've got ourselves. And the way we break out is by sticking in these T phi guys we had before, and then removing them again and replacing them with some inputs in inverted commas magic states. So this is kind of the main idea of a lot of papers, and there's been a lot of work on this, is you take your T phi guy, a bunch of T phis is enough. I don't think I actually said this anywhere, but if you have the Cliffords and you have some T phis as well, then you can do any unitary. So this completely breaks you out of this polynomial time kind of prison and allows you to do universal quantum computation if you have enough T phis. And then in order that we can actually do useful things on a classical computer, we then take away the T phis and replace them with these little gadgets. So you'll note that everything in this gadget is either a Clifford gate or a stabilizer state, apart from this measurement, this projector I do at the end. This guy here is a non-stabilizer state. So what we do is you take your universal, your completely arbitrary quantum circuit, you take all the T's out, you replace them with these gadgets, and then you get a quantum circuit which is Clifford operations acting on stabilizer states with these very specific non-stabilizer measurements at the end.
So it's the identity in the sense that all the probabilities are the same.
This is an identity of well, matrices essentially. Yeah.
Okay.
Like you can, this thing has a representation as a matrix. This thing you can work out what it does as a matrix here, and they're the same.
So just to be sure you have not lost the audience, could you ask the audience whether there are any questions so that they can hear us?
Yes.
So Grzegorz, could you say something that you are alive?
Yes, I'm alive.
Okay. So
Okay.
you don't have any questions.
Oh, not yet.
Good. So
Okay.
if you have, please do not hesitate to ask. So we
Yeah,
are in contact. Yes. Good. Thanks.
Yep. Yes.
This measurement, you need to do it like in the end, and you can do it. You need to do it every time you play a simulation.
You can do them all at the end. We never reuse these qubits, so we never reuse the measured qubits at the end. So it doesn't really matter where you put them, just as long as you measure after the C0. Yep. So I think, yes, here I have a fun slide, which is kind of what we're doing here. So we do, no. which wire do I need to change to
Yeah,
that one?
it's right.
Okay.
It's a condition.
Okay, it's not my fault. Yeah, so we have an entirely arbitrary unitary here, which is a Clifford followed by a phase gate, a Clifford followed by a phase gate, a Clifford followed by a phase gate until the end, with a measurement at the end. And we replace all the phase gates with C naughts, and then we do this non-Clifford, this non-stabilizer measurement right at the end here. So this process is Jagiellization, and it's not entirely clear that this has brought us anything like interesting, but I think it does, because what it buys us is that it buys us kind of a nice representation of a quantum state in terms of, yeah, a stabilizer state, which in some sense is a very simple object that we can say anything you like about. And these measurements at the end are also in some sense quite simple. They're all measurements in a basis which is orthogonal to the z-axis on a. So these are measurements in a basis which is somewhere on the equator of the Bloch sphere.
Sorry, yeah, but what do you do with those outcomes of measurements? How you use them in the scheme? You measure and what?
So it's just post-selected on this.
Do you mean these measurements, the A measurements, or the magic, like the magic guys? Okay, so what happens is you'll do this measurement in this basis, and you'll get one of two outcomes. If you get outcome 0, then you've implemented the correct gate, the T guide, which I have before. If you get the outcome 1, you'll implement a gate which is not the T gate, but differs from it by a Clifford, and then you have to apply a correction gate. Okay, yeah. So in this,
basically you modify your algorithm depending on the results of those auxiliary measurements.
Yes, exactly. So if you are really implementing a physical quantum computer, this is what you would do: is you would measure. If you get outcome 1, you have to do some correction Clifford. If you get outcome 0, you're happy, you don't have to do the correction Clifford. For us, we don't care because like in a classical computer, I can actually just apply a projector. Like I don't, yeah, I post-select by applying projectors rather than by like actually doing measurements. But yeah.
I call it similar to the standard teleportation scheme because you get 2 bits of information.
Yes, exactly.
And so having those bits, you possibly rotate your qubit or not.
Yes, yeah. I believe this Jagiellization also goes under the name gate teleportation. People call this thing gate teleportation. I, in some sense, am teleporting the T gate into the circuit.
So if it's also simple, why can't we simulate everything?
Because these measurements at the end take exponential amount of time to simulate. Well, maybe they don't. So, I mean, I had a question mark in my slide before when I said about the hills, right? So maybe there's a really fancy algorithm which can do these measurements in polynomial time. If so, we're all probably going to be out of a job because then you can do anything quantum in polynomial time on a classical computer. But I think the expectation is that there's no way to apply these measurements in polynomial time. So when we get to about here in the raw estimate and estimate section, I'm going to tell you the smartest exponential time algorithm we know to implement these guys. But for now, there's no polynomial time one known. Okay. So we do Jagiellization, yeah. And as I said before, this gives us a powerful representation of a quantum state because I can, a classical algorithm can prove stuff to itself about the stabilizer state, and it can prove stuff to itself about this non-stabilizer measurement at the end in polynomial time. And the stuff that the classical algorithm can prove to itself in polynomial time is, well, it's basically the output of our compressed algorithm. This is one of the algorithms in our paper. And what it does is it tries to reduce the number of qubits. So here I have 3 sections. So it tries to reduce the number of qubits in each section. It tries to reduce the number of stabilizers, which in some sense is replacing your state with a quantum state, which is a mixed one over a few subspaces. We have this compression number R. I will talk a little bit about R later, but in some sense, R tells you how boring your quantum circuit is. And yeah, the compressed algorithm runs in polynomial time. Yeah, which is nice. So one of the outputs of the compressed algorithm, or some of the outputs of the compressed algorithm, is a parity group, G, with T minus R generators on T qubits, such that this product here gives you your original computation. And I'm going to skip through this section fairly fast because I've already spent half an hour. So yeah, we have this little group. We want to compute then this sum, which is just expanding this guy out, expanding all these little terms out. And this sum here is over exponentially many things. It's actually over t minus r guys. And the fact that it's over t minus r guys is quite nice because it means that our algorithm will run very fast when r is very large. Because then when r is very large, t minus r is small. Note that r is always less than t, it turns out. Okay, so a naive runtime for compute just computes all the terms in this sum separately. And it's not very interesting. This is, I think, the best we had in about January last year. It turns out there's a much smarter way to do this, which is to compute the terms in the sum in a particular order. And I'm going to tell you where that order is. The order is basically so that you multiply one generator at a time to get you to the next term in the sum, right? And there's a particular ordering of the generators, which you can compute efficiently, which tells you how to do this. And the way it works is a bit like this. Oh, sorry. So this is what this does to this runtime. It makes the total runtime of computes into order 2 to the t minus rt. So once again, it's still pretty fast when r is very large. And the way this ordering works is by visiting vertices in a cube. So earlier we were complaining that we could only do landscapes that are 2-dimensional. Here we have quite high-dimensional cubes, but this is not so bad. So this function f, which tells you which term in the sum to compute next, is a path that visits every vertex in an n-dimensional cube exactly once. And then, yeah, you go up one, or you go in some direction, and it tells you which vertex to go to next, such that you visit every vertex in the cube, or in the like n-dimensional cube. And the way you do this, you build this path, is you build up the n-dimensional cube in terms of 2 n-1 dimensional cubes. So I start with a 0-dimensional cube, I clone it to make 2 points, and I join them together. This is a 1-dimensional cube. Now I clone it to make 4 points, and I join each one together, I get a 2-dimensional cube. Then I clone it, I join them up, I get a 3-dimensional cube, and then I clone it, and I join them up, and I get a 4-dimensional cube. And at this point, I give up because my slides would get too messy. But in my computer, I can do this quite efficiently for fairly large n. And this tells you how to build up your path. What you do is you have a path which takes you from here to here. Then you jump to this side, and then, so say my path and the 1-dimensional cube goes from here to here. Then you jump to this side, and you do that path backwards. And I jump to the 3-dimensional cube, I go here, and I do my path backwards. Yeah, it's inductive. It turns out there's actually a closed form for the path, but the idea from it is inductive. All right, so this gives you a nice path.
Classical computer, you told it's not a problem to generate many dimensional cubes. So practically, how far you go with n? Like 12, 50, 100?
Let me see.
Perhaps not, but 30?
50.
50.
We go to 50 in this graph, but you can go bigger.
We did no, you did 80 now.
Yeah.
Okay, but 30 is without any problem. Yes.
Yeah, sure.
But then 200 it would be difficult. Yes.
So it depends on your circuit, basically. So just doing the path through the hypercube is fine for 100-dimensional. This is okay. But you have to. But I actually want to do some computations, right? I want to do some math each vertex.
Nodes, yes.
Yes.
So which is already a number.
Yeah, but I have a closed form, so I just go through one by one. I don't have to store 2 to the 100 things. I store one thing and I update it 2 to the 100 times. It's okay. But yeah. So anyway, yeah. So this is his path. In fact, this path was, I think, first invented by this French guy, Edouard. He invented it as the solution to this time waster puzzle that someone had set him in 1872. And he used the same path again to invent his own puzzle, which is called the Towers of Hanoi, about 10 years later. Cool.
Well, when we ask if everybody knows how to play with the Hanoi Towers, yes?
I also do not.
One sentence to explain what is the object is.
So the object is to take all of these disks and move them to this peg over here, or to move them to either, it doesn't really matter. To move them, say, to this peg over here. And the moves you're allowed to do are to take a disk and put it either on the floor, on the ground here, or to take a disk and put it onto another disk which is bigger than it. So for example, if I move this top disk to this point, I then can't move the next disk down onto this one because disks are only allowed to go on ones which are bigger than them. So then my next move has to be to take this guy and put it over here. But then I can take this one and put it over here because it's smaller. And
And the optimal solution requires many moves. It goes like n factor.
2 to the n.
Is the number of rings?
I believe it goes like 2 to the n
Yeah.
because it's exactly this hypercube path. Yep. All right, cool. So anyway, this graph I really like because this graph basically shows our algorithm completely destroying the opposition. So here we have randomly generated circuits. So what I did was I took a bunch of qubits and I just randomly chose either Clifford or T gates to apply to each qubit to build up a big circuit. And these circuits all have 1,000 Clifford gates and 30 non-Clifford gates. And we measure 10 qubits at the end and work out the probability of some measurement outcome. And then I just increase the number of qubits. And you can see increase the number of qubits. This is the log axis, by the way. So increasing the number of qubits basically makes the standard sort of state vector simulation, where you store 2 to the n complex numbers, get exponentially faster, at least in this bit where the graph is linear. And increasing the number of qubits makes our algorithm faster. This is somewhat unexpected, but you know, it's pretty cool. And the reason our algorithm gets faster here is because the number r is getting larger. This compression number I mentioned before, r, is getting larger, and our algorithm scales as 2 to the t minus r times t. So as r gets bigger, 2 to the t minus r gets smaller, and our algorithm gets faster. So this, I think, is the graph that for me most motivates doing like weird and different methods of simulating quantum computers. Because like you can have a circuit that's maybe at 30 qubits here, which is completely unfeasible for a state vector simulation to do, like a normal simulator to do. But for our circuit, our computer takes 1,000th of a second. Our algorithm takes 1,000th of a second. But similarly, you could also have circuits which are very easy for the state vector simulation to do, and also hard for our algorithm. So different algorithms are fast for different problems. Okay, so I have about 20 minutes left, I guess.
You still have some 20 minutes. So.
Yeah. Okay. So so this is the first 2 of the algorithms. So there's 4 algorithms in our paper. So computer compressed the first 2. The main ones are called raw estim and estimate. So the way raw estim and estimate work is they take the second output of the computer algorithm, which is this quantum circuit W, applied to a magic state, and they express P as well. You can read this notation. You take your magic state, you apply a Clifford circuit, you do a projector at the end, and the norm squared of this vector gives you the probability. And here I have some different ways of writing this T guy. So it's a product of individual magic states on T qubits. You can write each of them in the computational basis, and you can write each of them in terms of plus and minus I states. And for reasons which I'll get into soon, it turns out this way is the right way to do this, even though these guys are not orthogonal. So what happens? You expand out this big product of magic states, and you get a sum of, again, 2 to the t terms. Oh dear. You get a sum of 2 to the t terms, each of which is applied to an input stabilizer state. Yeah, these are stabilizer states. So this is a t qubit state where, so if, yeah, sorry, the notation is a bit complicated. Y is a length t bit string. And if the ith bit of y is a 1, we have a minus I on that qubit. And if the ith bit of y is a 0, we have a plus on that qubit. That's all that happens. So basically, this looks quite similar to what happened with the compute algorithm. We took our big non-stabilizer thing, and we wrote it as an exponentially large sum over stabilizer things. Yeah, and it turns out that you can do this such that this P here is a normalized product probability distribution, which is handy. So in some sense, the magic state we want is the expectation value of some stabilizer state valued probability distribution. Yeah. I will talk more about this Xi guy now. So this Xi guy is what I called magic before. I promised I would define magic. So for the purposes of this talk, magic is this thing, where Xi of some input non-stabilizer state is given by this expression. These are the alphas I had before. In terms of the phase, so in terms of the angle in your rotation gate, it's this thing. And as you can see, it reaches its maximum at pi by 4. Yeah. And if you log Xi, you can think of this as a log psi as a measure of how far you are away from being a stabilizer state. So psi in some sense is an exponential of a distance. And it turns out the runtime in our algorithm is going to be exactly linear in psi star. Good. So what happens? The basic idea is that you take this exponential sum I had before, substitute it into the expression for p, and rather than do this for every single one of these y's, this 2 to the t number of y's, what we do is we sample a whole bunch of y's and assume that the sample mean is going to be close to the actual expectation value. Did you have a question, or you just said, yeah? Okay, sure. Okay, when I say assume, we prove some bounds. Okay, camel go grumpy. But like naively, if you sample enough guys, the expectation value is going to be close to the sample mean. We have some tight bounds. We have some good bounds on how good they are. So here are some tight bounds. I don't want to define any of the terms on this slide for the purpose of this talk, because there's a lot of them, and it would be a talk by itself. But the intuitive reading of this slide is that if I sample a whole bunch of vectors, the sample mean is close to the true mean. Okay, and this theorem by Hayes from 2005 lets us put good bounds on how close it will actually be. Yeah.
So say again in the plain words, this theorem says that if you take a bunch of random vectors, they will average out somehow?
Yeah, if you take a bunch of random vectors, the sample mean, so the average of them, will be close to the actual expectation value of the probability distribution you sampled them from.
Yeah. So in other words, you can say that if you have random mixed states composed of many random vectors, so then the mixture is close to maximally mixed state.
Depends on your probability distribution, I guess.
Yeah,
like,
but if you take the standard distribution generated by the Hall measure on the set of Q states.
Sure. You can do that. Yeah, then true. But I'm not going to do that. And my distribution is going to be this p guy that appears here. Yeah. But yeah, sure. If you pick them completely at random by the Hall measure, then they'd be close to the maximally mixed guy. Sure. Okay. Yeah, one thing to note is that here, here basically you can compare the norm of x with a. And so if your vector is very long, then this a is going to be larger and you'll require more. Basically, if the vector is very large, you require more samples to be close to end up being close to the mean.
Concentration of measure theorem.
Yep. And this upper bound here, so what's going to happen later on is this a here is going to be the epsilon in my estimation guy, and this thing on the right-hand side is going to be the delta. So my delta is going to be, basically this. So one thing that I didn't say is that computing the norm of this big sum is actually quite hard. So I want to compute the norm of this thing. Computing the norm as like an undergrad would involves just, taking the product of it with itself. But since the states inside these guys here are not orthogonal, or anything really, they have no nice properties. Doing the norm by just like taking the product with itself is really dumb, because it ends up with a runtime which is quadratic in psi star. So we basically steal this algorithm. It's from this paper by Bravi, Dan Brown, and people. They come up with a nice algorithm which is not quadratic in psi star. It's linear. This k here is effectively our psi star to compute the norm. And if you plug then the sampling algorithm with Hayes' theorem before, together with the norm estimation bit, what you end up with is this disgusting slide. I apologize for this slide. But basically, there's two parts to this. You have a failure probability here, which is when your sample vector is too far away from the actual expectation value. And you have a failure probability here, which is when your norm estimation estimates the norm boundary, basically, where the norm is further away than it's allowed to be. And so you have the two steps. Each of them has some error and some failure probability. You add the failure probabilities together and you get the raw estimate algorithm, basically. And this is really cool. I think this is where we were approximately 1 year ago with our work, maybe 13 months ago. And we were, to be honest, quite happy with this. But here I'm going to summarize. It has some good and bad features, this raw estimate algorithm I gave. The really good feature, the one I want to emphasize, is the runtime is linear in psi star. This is a massive deal. There were previous algorithms which were quadratic in psi star. And since psi star is essentially exponential, being quadratic in an exponential is really bad. But being linear in exponential is also really bad, but it's slightly less bad. The Theorem algorithm has this R in it here. It takes advantage basically of the compress algorithm. So if we didn't have the compress guy, the compress algorithm before, this R here would be replaced by a T. Oh yeah, I should say the exponential scaling comes because basically to make this exponential here small, S has to be of order psi star. You expand this denominator out, you get a psi star on the bottom, and you want S to be at least as big as psi star. Yeah. Okay, so it's complementary to the compute algorithm. So compute was good when R was huge, when R was big. Here, the scaling of this goes with R cubed, so this is good when R is small. The actual algorithm, like the constants in the algorithm, are very small. So not the big O statements tell you something about the overall scaling, but actually when you implement this on a computer, it doesn't take very many operations per unit in the big O statements. And yeah, it uses a polynomial amount of memory. So if you think about a state vector simulation where you just store 2 to the n complex numbers on your computer, this requires an exponential amount of memory, which is difficult. Our algorithm actually runs, although it takes exponential amount of time, it does take a polynomial amount of memory, which is kind of cool. It also has some bad points. So you have these S and L things that you have to input to it. And a priori, there's no really good way to know what the hell S and R are supposed to be. S and L are supposed to be. They depend on the unknown probability P that you're actually trying to estimate already, what the S and L are that you should choose. You have some epsilon here between 0 and the total error. And this basically says how much of the error you attribute to the sampling and how much of the error you attribute to the norm estimation. Yeah, and it's unclear how to divide this up. And it doesn't solve the problem statement I gave at the start with the P greater than epsilon being less than delta. It doesn't solve this problem because of this SNL, you don't know them. And the way we solve these is the estimate algorithm, which basically goes like this. If you don't know P, but you want to upper bound your failure probability, one thing you might try and do is just make P equal to 1. And this gives you a correct algorithm. The failure probability is a true bound, but it loses you a lot of performance. Basically because of how these guys are increasing in P. Yeah, they're both increasing in P. So if you make P really big, you'll overestimate your failure probability. So what we do is something slightly different, is you do take the upper bound of P as 1, but you allow a much larger epsilon than you were hoping for. So you estimate it with assuming the upper bound of P less than 1, but with a huge epsilon. Then you hope that this estimation gives you a new upper bound for P, which is less than 1, slightly. And then you run again with a slightly smaller error. And then you hope that this gives you a better upper bound, and you run again with a slightly smaller error. And you keep doing this until you've reached an error that you're happy with. And this is basically what the estimate algorithm does in a slightly more fancy way. Here are some plots. So you can see these red dots. Each red dot is its current best guess of what the probability is. The dashed line is what the probability actually was. We knew the probability already. And the triangles here are the upper bounds it manages to give each time. So it gets increasingly tight upper bounds on how good the probability is over time. And this graph is for an absolutely massive, like a very hard to simulate quantum circuit. It's got 50 qubits. It's got 16 non-Clifford gates. It has this fixed probability we did before. I said before. It's got 2,000 Clifford gates. Sorry. Yeah, and it ran in about 2 days. This is like 44 hours, I think it's, yeah, 1 day and 20 hours this circuit took to compute its probability.
What computer?
On my office computer. Yeah. So if you're trying to, so just imagine storing a state vector that contains 50 qubits. This is like 2 to the 50 bytes of memory-ish times some constant. This is way more than your computer can hold.
Plus 30 seconds.
Fun?
Plus 34 seconds.
Yeah. So yeah, the 34 seconds I include because basically the 34 seconds is this loop here, and the 2 days is the raw estimate algorithm running again, again, and again. So I want to just indicate how it's divided up. It spends almost all of its time querying raw estim with various values of S and L, and then does a little bit of overhead with the loop that I just gave you. Yeah, the estimate algorithm does something rather, actually slightly more fancy than I give on this slide, but this is the overall idea. It also like divides the error between the norm estimation and the sampling, and it does some other stuff, but this is basically the idea of what it does. Yep. So this is quite cool, I think. And this was some estimates. So basically what I did was I moved some of the stuff from the bad column to the good column. And I added some new bad stuff compared to estim. So the bad thing is the runtime is probabilistic. So the runtime depends on the sampling it does, which is kind of annoying. But because you do a huge amount of sampling, actually, it doesn't really impact it that much. Like if you take a very, very large number of random numbers, they're close to deterministic anyway. And the runtime depends on the unknown probability. So this second thing is a much bigger deal, is that a priori, you have no idea how long the algorithm will take to run. If the probability is really, really small, the algorithm will take a long time to run. No, if probability is very, very big, the algorithm will take a long time to run, sorry. Yeah. Okay, so this is all I want to say about Clifford+T estimation, really. Are there any questions about that?
Maybe
Okay.
from the outside.
Or even from the remote people, yes. Are you alive, the remote people?
Good question.
Grzegorz said he had to leave.
Oh, because Grzegorz is not.
Felix are there.
Is Felix paying attention?
9 people now. We took them.
Okay, it's possible that Felix is also left.
He's
No?
on, just, not listening.
Okay, fine. Well, that's his loss.
In the shower.
Yeah. All right, sure. So I want to just talk quickly. This is just 2 slides. So in addition to like the theory work, actually, Jakob gave a talk about this stuff at QIP last year, and some guys who work for IBM saw this talk and were like, "These algorithms seem great," and why wouldn't you think they're great? We want to add them to our library Kisskit. So who here has heard of Kisskit? Do I have to advertise that? No.
I've
Yeah, okay. So Kisskit is just a library, like a Python package for doing quantum computations. It's pretty useful. So I don't really know how to objectively measure the popularity of a Python package, but it got downloaded 50,000 times in the last month. So it seems pretty popular. You can do a lot of stuff with it. It's basically owned by IBM Research. They say it's owned by a community team, but if you look, every member of the community team actually works for IBM. So, apart from, no, not on their community team. I'm like a helper. So yeah, I'm implementing our algorithms for them, and so hopefully people can actually use them to do real stuff. Yep, so I wrote like half of it, I sent them the code, I'm waiting for some feedback on it, and then I'll write the other half, basically. I think this is a really like a cool thing for, a kind of unexpected thing for me is for my work to have maybe some impact on other people. This doesn't happen very often. People can actually hopefully use our algorithms and do like useful stuff with them, cool stuff. All right, so I have 10 minutes, 5 minutes, I'm not sure.
No, 5 minutes.
5, okay, so I'm very quickly going to talk to you about the new project I'm working on, which is fermionic linear optics, or Matchgates. So previously we had the Clifford guys, which could be simulated in polynomial time. A different thing you can simulate in polynomial time is Matchgate circuits, which are circuits made up of 2-qubit unitaries that look like this, with this determinant thing being very important. So these, again, are not universal for quantum computation because you can simulate them in polynomial time. It turns out that if you apply a little bit of trickery, you can map these match gates onto these fermionic circuits. So what you do is you build a little creation operator, which basically flips a 0 qubit to 1 qubit, and an annihilation operator flips a 1 qubit to a 0 qubit. And you add these phases so that the canonical commutation relations are satisfied. So what we have is like a spin chain of n qubits, and we have an A and an A dagger for each one. Which flips it, and each one, flips it from 0 to 1. From those A's and A daggers, you create some C's just by taking like even and odd combinations, basically, of the A's and A daggers. So for each qubit, you now have 2 C operators. And it turns out the unitary is fermionic if and only if you can, if and only if it has this action on the C's for a special orthogonal 2n by 2n matrix R. So again, this is a very tight restriction on the unitaries you can have, because initially you start with a unitary, which is a 2 to the n by 2 to the n matrix. And now I have a 2n by 2n matrix. This is way smaller. So we're in a sort of polynomial subspace of the full quantum theory. And this representation turns out to be very nice to work with. Yep, so there's this nice work by Toho and DiVincenzo, which say the Matchgate guys I gave before on the fermionic linear optics guys, these the guys that act on the C operators nicely, are exactly the same circuits. And moreover, you can do any simulations with them in polynomial time, basically. So this is basically the Gottesman theorem for Matchgates. Okay. So there's this nice paper from 2018 now, where these guys come up with invents basically what are the equivalent to the T states for fermionic circuits.
When this paper got published?
I think in 2019. I think it was on arXiv in 2018 and got published in 19, but it could be.
This is Barbara Kansas.
Yes. Yeah. Richard Josler, yeah. Yep. So they say if you take Matchgate circuits and allow input computational basis states, and you allow input states that look like this, then you can do any quantum computation. So this is exactly the same as the T we had before, the T5 states we had before. So I came up with this nice decomposition of this is the magic states on the left-hand side, and this is a sum. The magic state is a sum of two efficiently simulable guys. So you can, yeah. So we can basically play the same tricks before. We can replace each magic state with two efficiently simulable guys, with two fermionic guys. And then we'll end up with, say there's T magic states to start with, we'll end up with T fermionic guys, or sorry, we'll end up with two to the T fermionic guys when we multiply out the brackets. Yep. This is the idea. You can also do it in terms of density matrices. Again, I apologize for this slide. So this is basically instead of decomposing the magic state, we decompose the projector onto the magic state. You can do it in terms of the C operators I gave before. Yep. And there are problems with both of the two decompositions I just gave. So the problem with the vector decomposition, the first one, is that if you want to add up the results of applying like your circuits to two different fermionic guys, you have to have an algorithm that can simulate them in a phase-sensitive way, because the phase between the two obviously changes the output a lot. And no one has a phase-sensitive Matchgate simulation algorithm yet. We have non-phase sensitive ones, but we don't have a phase-sensitive one. So basically, like we have this algorithm gives probabilities, not amplitudes, right? It gives the norm squared of this thing, and we want an algorithm that gives the amplitude instead. Okay. This is what I've been working on, is coming up with a way to invent one. And then the issue with I think the issue with this decomposition kind of is obvious, right? It has 16 terms in. I don't think I want to work with this. And in particular, if you multiply out like T brackets that look like this, then your algorithm scales as 16 to the power of 2. It's not very nice. Okay. So yeah, very quickly in the last minute, I'll tell you how I'm trying to come up with a phase-sensitive Matchgate simulator. The problem with doing this is that the efficient simulation is based on this action where you stick a U on both sides with a dagger. And obviously, any phase information is lost in this representation, right? Because if I multiply U by a phase, U dagger gets the opposite phase and they cancel. So the basic solution is you fix the phase of U by fixing the action that it maps the vacuum state to the vacuum state. This gives you a sub-theory. And it turns out that this sub-theory is made up of guys whose R matrix is not only orthogonal, which I told you before it had to be orthogonal, but is also symplectic. So, okay, we want to know something about the real orthogonal 2n by 2n matrices, which are also symplectic. Does anybody know what these are? This is a famous result, but I didn't know it until August. Okay, the punchline, because this, a priori, this could be any matrix group, right? It could be arbitrarily disgusting, basically. But it turns out they're not, it's the unitaries. This is pretty magic, right? Under the mapping where you take like a 2n dimensional real vector space and make an n dimensional complex vector space out of it. So this is really nice, because we know quite a lot about unitary matrices. And we can maybe then say something useful. And this is kind of what persuaded me that maybe we can do something nice in this phase-sensitive simulator. To be explicit, because I like being concrete, the idea is if you take your R guy, it turns out it's a block matrix with blocks that look like C, S minus S and C, which obey these relations. And if C and S obey these relations, then C plus IS is unitary. This is how this mapping goes. Okay. So what's left over is some cosets. If you've been to Simon's talks recently, you'll know about cosets. So we have a group of guys which preserve 0, and we have some cosets of guys which don't preserve 0. I'm slightly over time, so I'm going very fast at this point. And it turns out we can characterize the cosets of the guys that don't preserve 0. They can all be written as a product that looks like this, where the lambdas are just some real numbers. So in some sense, up to equivalence of the symplectic guys, all of the non-symplectic guys look like just n real numbers, lambda. Yeah. And so this leads me to a conjecture, which I've been trying to prove for like a month now and haven't yet proved.
FLO, it stands for.
Pardon? Oh, fermionic linear optics, sorry. So this is a Matchgate circuit, basically, or fermionic linear optic circuit. They're the same for the purpose of this talk. They're exactly the same. Matchgate circuits are fermionic linear optic circuits and vice versa. Yeah. So yeah, so if you have a guide which is type 2, so it's not vacuum preserving, and it's actually one of if it's maximally not vacuum preserving, so anti-commutes with the symplectic form, then it can be simplified by 0 preserving guys to look like this. And this leads to the conjecture, which is any Gaussian fermionic state can be written in this form. For some complex number omega, a 0 preserving guy, u, and this stuff which isn't 0 preserving guy but is relatively simple. And if I can prove this conjecture, we have essentially a phase-sensitive Matchgate or phase-sensitive fermionic linear optic simulator. I have yet to find any states which can't be written like this. I tried quite hard. So I believe this conjecture is true. I'm currently working on proving it. Yep. This would be very cool. So I will leave you with my outlook. This says outlook section. So this is some other projects I've been working on. Yeah. This stuff I think is quite cool. Because these state vector simulations and Schrödinger-Feynman simulations are actually the ones that get used like in industry all the time. And I think it's possible to understand them from the same point of view as the kind of resource theory-based simulators, which I was talking about today, but no one's done it yet. And I would like to understand them. But for now, I will leave you. Well, now I'll leave it to you to ask some questions, basically. Now it's your problem.
Yes, thank you very much. So there's not much. Any questions from the audience? Far away.
Firstly, is there any audience far away?
Yes. Okay. Well, are you there? Is still somebody there?
Yeah, we can tend to see.
Yeah. So there are no questions at the chat. Are there any questions here? Local questions? Well, entangled questions, audience and people here.
Maybe I will ask them.
Yeah.
So how do you think this fermionic linear optic simulator could be? Why could it be better than the other one that you worked on, Clifford+T? Like,
I don't think
why
it's.
would it be useful to do this?
Yeah. So I don't think it will be better. What it will be is kind of orthogonal. So like the Clifford+T guy runs very fast if your circuit is close to a Clifford circuit, and it gets exponentially slower the further away you are from a Clifford circuit. The Matchgate simulator or the Matchgate plus Matchgate simulator will be very fast for circuits which are close to Matchgates. And as far as we know, these are not the same as the Cliffords.
So this would be better a simulator for a different platform, basically.
Yeah, exactly. So if you want to simulate circuits which are close to Matchgates but aren't, then this is what you use. Yeah.
Good. Any other questions?